Mercedes Richards received her PhD in astronomy from the University of Toronto in 1986. She's been a professor of astrophysics at the University of Virginia and a visiting scientist at the Institute for Advanced Study in Princeton, New Jersey. She is currently professor of astronomy and astrophysics at Pennsylvania State University. She lectures internationally. Perhaps her most unusual venue was at a month-long International Vatican Observatory Summer School for graduate students in 1999. The summer school is held at Castle Gandolfo, the summer palace of the Vatican. This is testimony to the fact that being a scientist will bring you amazing opportunities. She's the only person I know who has shared a summer vacation spot with the Pope. She's been involved in many math and science enrichment programs for high school students, including the Vermont Mathematics, Science, and Technology High School Summer Institute, where she has already spent a week this summer. We're very pleased to have her visiting the UC Davis Cosmos program. Her work on flare activity in binary star systems was featured in Science News Online in August 2003. The title of her talk today is From CAT Scans to Astrotomography. Please join me in welcoming Dr. Richards.
Well, thank you all for inviting me to give this lecture. I'm a little bit nervous, but I'll be just fine, I think. Well, today I'm going to talk about tomography, the technique of tomography. And basically, this technique is one of the most fascinating techniques that I've ever come across because it spans so many different regimes. Before I start, I'd like to give some acknowledgements to a wide range of people and sources. Basically, I've taken a lot of the first part of my talk from internet sources, and the last part of the talk is really based on my own personal research. This work has been funded by several federal funding agencies, the Air Force, the National Science Foundation, and NASA, and also through a grant from the Institute for Advanced Study in Princeton, plus observational grants from the National Solar Observatory and Kitt Peak National Observatory. And I've had many collaborators involved in this work, which goes back for some 10 years. Several undergraduate students, Bob Jones, Larissa Bowles, Larry Moore, graduate students here listed, Albright, Ratliff, Swain, Kempner, and Kolkar, and senior researchers, Pavel Kupski, Wojtek Szymon, Gerald Lee Peters, Rukio Hirata, Peter Skoda, Seiji Musada, and Jan Budai. You'll see that this is an international collaboration in some cases. This technique of tomography that I'll describe today is really what I call magic. And it's really unique that the letters MAGIC spell out the various disciplines that are used in tomography or that have been applied to tomography. First, mathematics, astronomy, geophysics, internal medicine, and computing. In fact, I believe the very first application of tomography was when Aristotle, back in about 350 BC, realized that during a lunar eclipse, you have the curved shadow of the Earth seen against the face of the moon. And you can see that clearly here. As you go through the eclipse from the beginning all the way through, you see the shadows here. They're not perfectly curved with a little bit of fuzziness because of clouds and haziness in the atmosphere. But as you progress through the eclipse, it's quite clear that you have a curved shadow against the face of the moon. Aristotle felt that the only reason why you were seeing these curved shadows was because the object that was producing the curved shadows had to be a sphere. In other words, the Earth had to be a sphere. In order to illustrate this, I just wanted to show you, here I have my ball, and as you can see that here is a sphere, and the projections of the sphere are clearly circular. If you put another object here, a star that doesn't give you a curved shadow, I have some other ones, no curved shadows. Even a cube, no curved shadow. The only object that gives you a curved shadow is a sphere. Now unknown, can you all see that? Okay, good, perfect. Unknown to, I like playing with toys as you can see. I think unknown to Aristotle, what he was really doing was adding up or summing all of these curved shadows of the Earth, and these are all seen at positions around a circle, and you can sum them all up to produce a sphere. I'll show you how that works. Tomography, this word tomography that you're going to become very familiar with by the end of this talk, is really a technique that's used today to make three-dimensional images from really two-dimensional pictures or slices. The word tomos means slice or describing, and the part graphia is just the other part of the Greek word that means describing. So tomos is slice or section. And the projections, as I just showed you, are like shadows, right? You can have different objects. For example, a sphere would produce a shadow that's a circle. A cube would produce a shadow that's a square. And in the case of the human body, with use of X-ray pictures, we get this projection. And in astronomy, we can actually study how gases flow between stars by using a projection that's just the spectrum of light. All right, let me just explain how this works. Someone by the name of Johann Radon, he was actually a mathematician born in the Czech Republic, but he spent most of his life in Austria. And so he's actually known as an Austrian mathematician, but he was born in the Czech Republic. And back in 1917, he was the first person to actually formulate a mathematical equation to describe a projection. This is how a projection works. Let's say you take a light bulb and you project, oops, I'm not sure you can see a cube up there. It looks pretty dark from here, but you can actually project this light onto your three-dimensional object, which is a cube in this case, and you get a two-dimensional projection, right? That's just a square. Next, so that's your projection. But usually what happens is that you really don't know what this three-dimensional object is. All you have are the projections, right? So you end up with the projections, just as in the case of the Earth, where we only saw the shadow of the Earth against the moon. Most of the time, we only have projections, and we need to know what this three-dimensional object is. So there's a very good way to recover this three-dimensional object, and the way you do it is in terms of a process that we call back projection. With back projection, you take the individual projections here. Here's a purple one, for example, and you basically slide the image toward the center of the circle. You again move to the next projection, you slide it in, and so on. Basically, what I'm trying to say is that in order to recover a three-dimensional object, you need to take projections around the object. So you get these projections around the object, around a circle basically, and then you force them all back toward the center of the circle and you recover the three-dimensional object. So the result, which on your screen looks a little dark, is actually this cube right here. So this is the reconstructed image, which we also call the inverse Raton transform. Okay. This is the only mathematics I'm going to show you in the lecture, but it's really important just to describe roughly what Radon wrote down in his mathematical paper. So he started out by saying we have a three-dimensional object, and it's going to be described by this function z equals function of x and y. So we're basically looking at this three-dimensional space here. The Raton transform is just a two-dimensional projection. And it's going to be described by this function g of S and theta. I'll show you what these are. If you consider a line, right, you all know what a line is, right? This is my red line, and it has the perpendicular distance, which you can't see quite clearly on your screens. But this perpendicular distance from the line back to the origin here has a length s, and the angle from that line to the x-axis is called theta. So we can describe the distance s in terms of x and y coordinates and the angle theta. That's the description of our line. And so we basically, the two-dimensional projection g is just a double integral over two directions of this three-dimensional function. Very simple, right? It's not that complicated. I know it might be terrifying at this point in the lecture, but it's very simple. So we have basically, in order to understand how the Raton transform works, it actually works like an on-off switch. I actually show you here. Here's a surface of a three-dimensional object. It doesn't look too three-dimensional right now. If any line passes through the object, then basically the Raton transform will behave like a very sharp peak. We'll have a very sharp peak, or it will show up as a bright image. And if the lines do not pass through the object, as in this one here, then the Raton transform will be almost like 0. So it's pretty much you pass through the object, very sharp peak or very bright image. You don't pass through the object, it's very dark. And so you can get from this very pattern, of ons and offs or brights and darks gives you very sensitive information about the shape of the structure, of this three-dimensional structure. So that the Raton transform is really beautiful in that case. Right. And just to completely frighten you, I'll just show you the complete mathematical form for those of you who are practicing mathematicians who need to see this equation, right? The full form of the Raton transform is in the first yellow box up here, right, without the integration over the line. And then to invert it, we just do some integration here. Okay? That's all you need to know. But I've described to you the very simple process of tomography. All right? Basically, just summing all of these projections, you can recover the original source. All right, let's give you an example of what happens if you remember, in order to recover this three-dimensional object, you need to take projections at positions right around the circle. Well, what happens if you don't have enough projections? Well, in the first case here, this slide shows you what happens in the first box if you only have one image. Well, if you have one image, you haven't recovered very much information. But as you increase the number of projections, say down to 15, you begin to see a very interesting picture. This is what my face looks like about 6 o'clock in the morning. I look like I have one square eye, one round eye, not completely alert. But this is really the effect of having projections. There's another interesting thing that we can do with the Raton transform before I show you some applications, is that we have discovered that when you're doing the integrations, remember I showed you that in order to get the projections, you have to integrate over the x and y directions. Remember that? Well, we were doing integrations along infinitely long lines. And so it turns out, what this picture is showing you here is that if you start out with a test image, here's your test image right here. It's just this inverse V shape. If you use the traditional integration over infinitely long lines, what you get is an image that's actually an X. It's incorrect because you've integrated over lines that are just too long. The object is very small, you've integrated over lines that are too long. But if you restrict the length over which you integrate, you can actually come up with a pretty good reconstructed image. And here it is, what we call, it's a process that's called a localized, using the localized Raton transform, instead of integrating over infinitely long lines. So let me give you some examples here. On the left, I show an image of the Pentagon. And we can take pictures of this pentagon at positions around the structure, this five-sided structure. If we use the normal Raton Transform process, integrating over infinitely long lines, we can actually get a picture that looks pretty scratchy. You get the sense of a five-sided figure, but it's not precise. However, if you integrate over lines that seem to be a little bit more precise, you know, the Pentagon is a large building, but it's not a mile wide, it may be half mile wide, but something that's not infinity. If you use integrations over those shorter lines, you find that you get a much more precise reconstructed image of the Pentagon. Similarly, this work has been used by the National Security Agency. This is not classified, or I wouldn't be able to tell you about this, but there are several publications. The reference here you can't see because the writing is a little bit pale. But there's a group led by Copeland who've done this work using localized Raton transforms, and we can actually look at this image on this right here. If you look at this image, you're basically taking a picture of the surface of the water, right? The seas near the coast of the United States. And if we wanted to check to see if there are any submarines or ships that are not supposed to be anywhere near the coast of the United States, maybe foreign ships, then the United States military actually, they scan the waters and they can get images like this one. Here is a satellite aperture radar image of a ship wake, and you actually see this very faint structure like this in the water. But if you do some images, if you take projections of this image around this structure, you can actually reconstruct a very sharp and well-defined image of the bow of a ship. So you know a ship was here. So the military is using these techniques right now to make sure that we don't have any surprise attacks from foreign or even currently friendly countries. All right. Well, let's get into the actual applications of tomography. Tomography has been applied to many different areas. Medicine is the most popular one. There's geophysics, oceanography, archaeology, and most recently, astronomy. In medicine, you know, it's interesting to meet people on the street and you say, have you ever gone to the hospital? How many of you in the audience have ever been to the hospital and had a CAT scan? Oh, 2, 3, okay. About 10 people here. Very good. Well, the older you get, the more of them you need. Well, it turns out that the acronym CAT really means computed axial tomography. Right? Computed axial tomography, that's what it means, CAT. Sometimes they use the word CT, but it's really a technique of tomography in which they're using X-rays to make these projections. In the case of magnetic resonance imaging, what we found is that by using magnetic fields instead of X-rays, we can get much more precise images of the internal structure of the body. And so magnetic resonance imaging has also been used with the aid of tomography to make images of the internal structure of the Earth. I will go through the different applications in turn. Okay, good. Here in the case of the human body, typically we can take, remember, in order to reconstruct images of the body, we need to take projections around a circle. And so there are 3 different dimensions in which you can take these projections. In medicine, the preferred direction is really the axial direction, which is this direction across the body. That's the blue. That's the blue square there, partial blue square right here. That's the axial direction. And that's why when you get a CAT scan, it's called axial tomography, computed axial tomography, because the images are all being taken in this plane and around, at angles around that plane. There are other machines that can be used that will take coronal pictures. So those would be coronal tomograms. That's the yellow rhombus or whatever four-sided structure there, that is. And so those will be images across your body in this direction. You can also take sagittal images in this direction. And so it's just traditionally that most of the machines, the tomography machines, have been set up to take axial images, and that's why they're called CAT scan machines. But there are now, for example, this picture here shows that you can actually stand up and get both coronal images as well as sagittal images in this picture here. And here, just to show you how beautiful these are X-ray images of the body, but we can actually take CAT scans of the head. This one here would be an axial scan. This is more like a coronal scan across the lungs. Well, here it is, right here. And this last one would be a sagittal scan right across down the head. The lower images here really are, you can tell the improvement in the quality of the images because we're using magnetic fields here. I wanted to just give you a sense actually of how much work has gone into this technique, the history of medical imaging techniques. And it actually all started with Röntgen. William Conrad Röntgen actually discovered X-rays in 1895, and he realized that you could use X-rays to take pictures of the body. He actually won the Nobel Prize for physics in 1901. This is a real trail of Nobel Prizes here, with the exception of Johann Radon, whom we've already spoken of. He was a mathematician, and mathematicians don't get Nobel Prizes. But he actually was very influential in this whole development of tomography. Along came, so this is Röntgen here, then we already have met Radon. Over here we have Alan MacLeod Cormack and Godfrey Hounsfield. Cormack and Hounsfield worked together basically in two different directions. Cormack realized that, since X-rays were first discovered in 1895, this was back in the 1960s, he started working on ways in which you could improve the X-ray pictures that were being taken. If you want to improve a technique, there are two ways to approach it. You can actually improve the computational design. You can improve your equipment, right? There are different ways of approaching the problem. So Alan Cormack, he improved the computation of the tomography from the X-ray images. And Hounsfield came along and he said, well, we got to make better images, so he built better machines to make better images. And together they won the Nobel Prize for Physiology and Medicine in 1979. Paul Lauterbur and Sir Peter Mansfield just last October got the Nobel Prize for Medicine because they applied this magnetic resonance imaging to the whole process. So they realized that magnetic fields could be used to make more precise images of the human body than X-rays. Okay, so that's medicine. In archaeology, we call this archaeotomography. This technique of reconstructing three-dimensional structures from projections has been quite useful because in archaeology you don't want to, take a hammer to your instrument to figure out what's on the inside. Right? This is a precious artifact that you've just discovered, but it would be interesting if you could find out what's on the inside. So tomography has been applied in several cases, where we have these structures like this, statues or heads, or even a preserved body like this one. But the best case, the most recent case in which tomography has been applied, and successfully, was when in the case of the Iceman. This is a 5,300-year-old, perfectly preserved specimen that was discovered somewhere between the Italian Alps and the Austrian Alps. And this is about 4 years ago. And there was a scar on the back of this specimen. The left part of this specimen's back, there was no line going through it, as you see in my picture. But there was a lot of controversy as to the source of this scar. Was this guy killed in a fight? Did he die naturally? did he prick himself on a thorn? Who knows? Well, tomography was used successfully in this case because they took X-ray images of this structure and discovered the image of an arrowhead embedded inside his body. So we know for sure that he was killed by aggressive forces, non-friendly forces. So that's one wonderful case. All right. In the case of geophysics, we talk about seismic tomography. And in seismic tomography, really use the basic seismic waves. We're in California, so you all know about seismic tomography, don't you? Earthquakes. There are a bunch of really strange people, right, who whenever there's an earthquake, they run toward the source while the rest of us sane people are running away. And we are grateful to these crazy people, these crazy geophysicists, because they have helped to provide us with very sensitive information about the internal structure of the Earth. We use in seismic tomography several seismic waves. They're called the P waves, S waves, L and R, primary, secondary, love, and Rayleigh waves. And the P wave is very much like, it operates like a slinky. Like how an earthworm moves through the ground, you have these compressions that travel all the way through the Earth. And in the case of P waves, they travel through both solid and liquid. We have S waves, shown in the second diagram. S waves behave like waves on the top of the water. And the S waves are the second wave that you feel during an earthquake. The P wave is the fastest. It's the one that gets there first. The other waves that are really painful are the love and the Rayleigh waves. These are surface waves, and I try to show you here. In this picture, the love wave is the fastest surface wave, but it sort of moves the ground sideways, moves in and out like this, while rolling up and down. But the Rayleigh wave is the scariest of the whole bunch because it rolls. That's the one that really makes your house shake during an earthquake. The love and the Rayleigh waves haven't provided us with as much information as the P and the S waves. You can see here a seismograph. Here's the P wave, the very first wave. Then we have the S wave, a little bit bigger. And then by the time you get up here, that is the Rayleigh wave that you're seeing here. You can see how strong that is. But we've been able to detect the internal structure of the Earth to precise accuracy. The way it works is that when at the site of an earthquake, here we go, here's the internal structure. At the site of an earthquake, which is somewhere over here in this picture, they put up a whole bunch of instruments, and they also put down measuring instruments, seismographs right around the Earth. If the wave passes through any liquid structure at the other end of the Earth, you would only be able to see primary waves, as in this case over here. But if it passes through only solid, you'll be able to see both primary and secondary waves. So we now have if you see the lower right image here, we now have very detailed internal structure of the Earth. There is a solid core in the very center, then an outer molten core of iron, and then above that we have a mantle. There it is, the mantle, and then finally the crust. We know exactly how long that is. It's about 6,400 kilometers in radius, thanks to this seismic tomography. Taking, again, this collection of seismic information around the entire surface of the Earth. And there are lots of things we do with seismic tomography. More recently, we've been able to detect the structures, continental structures below the crust of the Earth. These are in these pictures here on this side of the page. Those structures are not on the crust, but below the crust and in the mantle, upper mantle of the Earth. And we get that information by studying the love and the Rayleigh waves. Okay, we've talked about so far medicine, the application to medicine, archaeology, geophysics, and now I want to talk about the application to, we're getting closer to applications to astronomy. We can in fact use radar to get sensitive information about positions. And the way in which we do this is quite simple. Radar, I know if you talk to people, typically, high school students, even college students, you ask them, do you know what radar means? And they'll say yes, or they won't answer. But a lot of people really don't know what it means. So I've spelled it out here. Radar is really an acronym. It's not a proper word. It means radio detection and ranging. I've underlined the parts of the words that spell out the acronym. And then there's also another type of radar that's called SAR and SIR. The SAR are the synthetic aperture radar, and SIR are spaceborne imaging radar. All of these are quite useful in tomography. For example, well, let me explain first. How does radar work? Basically, with radar, you bounce a radio wave off a surface, and you actually measure the amount of time it takes for the wave to get back to you. If the object actually moves away from you, then it takes longer, right? And if the object gets closer to you, then the radio wave gets back to you in a shorter time, right? So you have just the change in the amount of time it takes for that sound wave to get back to you gives you very detailed information about the shape of that structure, right? For example, the Titanic, the famous Titanic, was discovered in 1985. The position of the sunken remains of the Titanic were discovered with the help of radar, basically bouncing radio image. They had to really scan a very large section of the seabed, the ocean floor. They knew roughly where it was, but within several tens of miles, and they had to scan a lot and literally use this technique of tomography to definitely identify the source. So that was done with radar. We can also use radar to get images. This is synthetic aperture radar images of the Earth. Now, in the case of the Earth, we don't need radar. We can take real pictures, right? We have satellites out there in space taking real pictures of the Earth. But this is really used as a test to see how well the procedure works in space, where we can't get beautiful pictures around the Earth, real pictures. So these look like they are real pictures of, this is a riverbed. This is the Danube, the famous river, Danube River. This is near Belgrade in Serbia. But this image was made by bouncing radio waves off the surface of the Earth. So it works very well, and so we have this beautiful tomographic reconstruction of the surface of the Earth. And there's also a volcano on Isla Isabela. All right, well, how does this work? Oh, I'm showing you my movie already there. But in the case of astronomy, let's look at the planet Venus. Venus is covered with a very thick layer, here it is, a very thick cloud layer that contains carbon dioxide and sulfur dioxide and sulfuric acid. And from the Earth, Venus looks very dark. You cannot see below that surface if you're looking at it with a regular telescope, with a regular camera. However, if you bounce radio waves, if you use radar and bounce those waves off the surface of Venus and do it around the circle using tomography, you can reconstruct this beautiful image that we see here, the image to the right. That's the image of Venus, which shows continental structures just like we have on the Earth. The only difference is that the blue surfaces, that the blue regions you see are not oceans. They're just that solid crust. That's just colored to show the contrast in the different heights of these structures. The second largest mountain in the solar system is called the Maxwell Mountains, and it's way up here, this enormous structure. It's much wider than Mount Everest. And this movie that you saw earlier was taken it was made using the technique of tomography with a satellite that was called Magellan. That was about 8 or so years ago. All right. Right. Well, in the case of astronomy, I'm showing you this beautiful picture of the sun. And in the case of astronomy, we are fortunate that we have a very large star near us that's called the sun. We have satellites. For example, this observatory called SOHO, Solar Orbiting and Heliospheric Observatory, that's out there right now taking pictures of the sun right now for today. In fact, the movie that you saw is constructed from a set of images of the sun that were taken just last month. I would have done the one for this month, but it only came out 2 days ago, and I didn't have time to download it. But this is a recent picture of the sun, and SOHO provides us with those images. However, we're not as fortunate in the case of the more distant stars. Distant stars, if you look on the right, here's an image here. In the case of the distant stars, we look out and we see dots of light. A lot of these dots of light actually contain more than one star. But even with the largest telescopes, we can't separate those stars. The word we use is that we can't resolve them. Okay? And even though they actually might look like this image here, with the largest telescopes, that's what they look like, a dot of light. So we have to use tomography in some interesting way to find out how the gases are flowing between these stars. We use, in this case, a slightly different procedure to make the reconstructed images, to make the tomograms. In all the other cases, what have we done? We've used X-ray images, right? Two-dimensional X-ray images, and we splice them together around the circle to make a three-dimensional structure. We've done it in medicine and in oceanography and in geophysics, even with the seismic waves, with radar, with sound waves. We can do it to reconstruct some three-dimensional structure. But in astronomy, we're stuck. We're in deep trouble. What do we have? We can't take a two-dimensional picture of any kind, because you take a picture of a dot, you still get a dot. So what do? The only information that we really have from these distant stars is in the spectrum of light, right? You know what the spectrum of light is all about, right? I use my slinky for multiple purposes, right? It can be P waves or it can be a spectrum. So the spectrum of light goes from blue to red, right? In astronomy, what we have realized, actually, the physicist Doppler found this out for us, that when an object is moving toward you, the wavelengths are shifted towards shorter wavelengths, so everything seems shifted toward the blue. And when something is moving away from you, the light is shifted toward the red. So something is moving toward you, it's blue, then red, away, toward, away, toward, away. The whole spectrum is shifted. And so what we have done in astronomy is to try to observe a bunch of stars that we know are actually double. And we look at we observe these systems. There are a bunch of stars that are actually called binary systems, right? In the case of these, they're actually eclipsing each other. And I have my two stars here. So in the case of an eclipsing binary system, one star would occasionally block the light of the other. And so because they're doing this, that gives us a way of actually applying tomography. See, the neat thing is that when you're in the case of medicine, the patient is on the table and you can take the pictures around the patient. In the case of the Earth, the earthquakes are happening all over the place, and we can literally travel from one place on the Earth, so we can actually get those images around the Earth. And in the case of Venus, we have the satellite Magellan go and take images around the planet. But in the case of distant stars, we can't even do that. We can't get anywhere near there to take pictures around the object. So what do? We try to find objects that are moving relative to us. Okay, so we find these eclipsing stars and we look at them and we can use the spectra to make images of these systems. Here, for example, is just the very best that we can do the very best that we can do in terms of taking real pictures to separate these stars. But we can, in fact, now use this technique of what we call Doppler shifts, right, to give us a sense of how things are moving relative to us. We can apply this to cool stars like our sun. All stars are spinning. And so if they're spinning, that's another way. They're spinning, we can see different parts of these stars. And so we can actually, go back here and show you those movies. We can actually make beautiful movies of images of stars now. And lots of stars that are like our sun, a lot younger than our sun, they have very big spots. That's what we've discovered. They have very big spots on the surfaces near the poles. You can tell look at these beautiful pictures. In the case of our sun is this object here with some wimpy little spots down here. Right? Now these are really young stars. This is what our sun looked like when it was a lot younger. This is what we've discovered. That our sun, when it was a lot younger, had enormous, huge spots near the poles. But now that it's older, it has just many fewer spots, and it's actually spinning slowly. Okay. In the case of pairs of stars, we call binary stars, I said we can look at the spectrum. I'm not sure how clearly you can see this, but here are the two stars. These stars are so close that one star is actually losing gas to its companion, and we can, because these stars are eclipsing, we can take pictures or spectra. These are images of the gas flows around this system. And I explained earlier, for this star, this gas that's moving around this one star, we can make a picture of that gas flow very easily if we use the same Doppler technique. Here's a central star. Typically, this flow of gas will form a ring in this left image here. And here's this ring. The part that's moving toward us will be blue shifted. The spectrum will be shifted to the blue, and the part of the ring that's moving away from us will have a spectrum that's shifted to the red. So we look at that pattern and we make these images. We can get rings like this. This is a Doppler tomogram of what we call a group of binary stars that are called cataclysmic variables. And this movie to the bottom lower right shows you roughly how these variables are formed. They have mini explosions sometimes every day. And you can see this is quite powerful because you have this enormous star losing gas, forming a ring around the companion, and every now and then when you have an explosion, when the ring gets very compressed, very dense, you have an explosion and the whole ring blows away and then reforms, blows away and reforms. And these are called cataclysmic variables. The best we can do is so this is a much cruder version of that nice movie. But the best that we can do with tomography is to actually identify just rings of gas. So what you just saw in that movie is an artist's conception of what should be happening. But this is the real thing here. This is the real thing. This is what we get from studying the spectrum of light that comes from the system. We get this ring of gas, we actually can see an image of the star, and actually in cases where the central star is what we call a white dwarf, right? It's a very, very compact star. If that white dwarf has a very, very strong magnetic field, it turns out that we can actually see the pure flow of gas between the stars. That's this beautiful flow here. In this artist's picture, it's that flow there, right? This is what we call the gas stream. And it actually demonstrates that gravity works. Basically, what's happening between these stars is that you have the gas falling. Except the only reason why this path is curved is because the whole system, the whole binary system is moving. And so that path is curved for that reason. And so it's really beautiful that we can actually make images of these flows of gas. We can also make images of, and actually model how the ring of gas, you could see the lower right image, how that ring of gas brightens over time and changes before it blows away. We also have a group which are, these are my favorite objects, the Algols. This is another group of binary stars where you have one blue star here and a star like our sun. And things are a little bit more interesting here. The reconstructed image of gas flows in these systems, it shows a range of structures. I'll explain them shortly. You can see them all here. But we see images of, we can actually detect the presence of the sun-like star. If I get my mouse together, we can actually detect the flow of gas between the stars, demonstrating that gravity works, because that flow, if you look at this picture here, I'm going to show you a movie shortly, but okay. If you look at this stream here, that's the predicted path. So we work out the mathematics, we know how gravity works, and we notice that the flow that we detect, this tomogram, actually is sitting right on top of that. So we know that gravity works out there in space the way it's supposed to work. And it might sound like a silly thing. Obviously gravity works. But the thing is that we're not sure if any of these stars might have very, very strong magnetic fields. If they have very strong magnetic fields, then the magnetic field might actually push the flow away from the pure gravitational path. So we're just checking to make sure that gravity works. But it's a beautiful confirmation of this. And these systems can be separated into two groups. These stars, I'm talking about the blue and the red here. You have one blue star, one red star, and if they are far enough apart, they will actually form a very nice, beautiful ring around the star. And when they do that, these are the observations here. This is the hydrogen line that we're modeling. This is the blue shifted part, and that's the red shifted part. So this part is coming from the part of the ring that's moving toward you, and that part is coming from the part of the ring that's moving away from you. So we just look at these lines, and it gives us a lot of information about the rings. In some other cases where the stars are very close to each other, you can see that here there's not enough room for this flow, this what we call the gas stream, to go anywhere, and so you get a very, very weak signal. No nice rings are formed, and instead we basically get an image of the cool star here. This is really hard to understand, these images, because these tomograms, because they're in dimensions of velocity, right? We don't see things normally that way. They're in dimensions of velocity, and so we have to try to use helpful aids to understand what's going on, right? So here is this lower image here. We have a bunch of systems that are called the alternating algols, where sometimes you look at them and you get this image of a nice, well-formed ring, and then other times the ring disappears and all you see is a gas stream. Ring to gas stream. So I'm going to speed this up a little bit here. In the upper image you see, as the ticker mark moves along, you see exactly the spectrum of the hydrogen line that we observe. And basically all we're doing in this technique in astrotomography is we're just adding up all the velocities that we get from the two lines. You have the two lines and they get shifted back and forth like this, one from the blue side, one from the red side, and you just add them up as you go around the circle, and that's how you make your image. It's really a beautiful, nice technique. In order to understand, and actually in order to interpret what the real observations are telling us, I had to make a minor diversion to do some theoretical simulations. So these are numerical calculations that try to explain what we're seeing, right? Because when we do the tomography, we actually have this image here that's on the right. We know we have a velocity image in Vx and y coordinates, and we want to know what it would look like in x and y coordinates, the way we normally see things. And so this was the purpose of these simulations. So we actually did make movies of this showing how the flow occurs, and we can actually trace that flow in normal xy or Cartesian dimensions, as well as in velocity dimensions. And then we also try to make the tomogram the way it's really made. You see, what happens is that in order to make one of these tomograms, it looks like a nice movie and it's really beautiful, but you know, I've had to use thousands of observations of stars just to make some of these tomograms. You go out and you observe the stars, you get the spectrum of light, and you basically observe for a whole week. You observe a binary system for a whole week, and then you slap all of these hundreds of observations into a single picture to make that tomogram. And so we did the same thing with these simulations. So we're calling these simulated tomograms, and we made images here to show what this tomogram should look like, and we can control the conditions under which we make these. So for a very wide system, this is a wide binary, call it TT Hydra. The two stars are very far apart, so we expect a ring to be formed, and in fact we do get a nice ring. In the case of a system that's a little bit closer, the gas stream is going to hit the surface of the star, and what we find here is that you get this weird structure. It looks like a ring, but the brightest part is actually this gas flow between the stars. And in fact, the ratio of the brightness between the two can change depending on how fast that flow is, the gas is flowing between the stars. So when the flow is small, this is when the gas density is low. When the flow is small, you basically only see that gas stream. The other structure is there, but it's about 100 times fainter, so you don't see it. This is what you expect in the real observations. But in the case where the density is higher or the flow is faster, you see both the stream and the disk. And so this really explains what we're seeing in these alternating algols, that when sometimes you see a stream, then a disk, and a stream and a disk, what's really happening is that the flow, the speed at which the gas is moving is changing, and it's changing overnight. Can you imagine the sun, you know, two suns in front of you, and one is losing gas, and this speed, the speed at which the gas is flowing is just moving so fast that it's changing overnight on you. This is really a very beautiful and awesome thing. So I'd like to end my talk by saying that right now we're at the edge of the state of the art of dealing with tomography as it applies to astronomy. And what we really like to do, we have used simulations to try to understand, to try to interpret these observed astrotomography images, but right now we have not yet been able to find a way to convert these velocity images into real Cartesian images. And when we do that, I'll be the first one in line. We probably need a spaceship to take real pictures right now, but I can guarantee you that there's a mathematician out there, it may be even one of you in this room, who might end up providing us with this critical mathematical formula that will help us to convert the velocity images to Cartesian images. Well, thank you very much. How did I get interested in tomography? Well, it's a long story that I really don't understand. You see, it really, you think it's funny, but in many ways, when you're doing research, you're never quite sure where it will lead. And when I was in graduate school, I was actually interested in studying these eclipsing binary stars. And I had actually collected hundreds and hundreds of spectra of these systems. And for my PhD thesis, I had to try to make a model of what was going on, just based on staring at hundreds of spectra. And it was kind of scary. It took me 2 years. You know, I sat there staring at these little wiggles and wobbles in the spectrum. You've seen some of the ones I showed you earlier with the little bumps in the lines, and they changed into all kinds of strange shapes. And I said to myself, I could come up with any model based on what I'm seeing here. And that model would basically be biased because if I wanted to look for some kind of ring around the star, I could find the double peak lines all over the place. And if I wanted to find the flow of gas between the stars, I could find, just the right shapes to produce that. And so somewhere inside me, that was good enough for my PhD. That was a lot of work for my PhD. But even after I finished that work, when I became a professor, there was always this question in the back of my mind, what if I'm wrong? Right? And that's the question. You think that because you're in high school that this question will go away. Well, the higher up you go in the research ladder, the more this question haunts you. What if I'm wrong? It's going to be very embarrassing because you're so much higher on the ladder. You go, oh, big drop. Anyway, so I discovered this technique of tomography because it was one way in which I could use all these spectra, these observations, and I could use them in a way that didn't include any personal bias on my part. Okay, so basically all I'm doing with tomography is I'm getting the spectra, I'm summing them up, I'm really converting, I have the shifts of the velocities there, and I convert this one shift into the x and y coordinates, and it's a very simple deal. I don't have to say I'm looking for a gas stream or I'm looking for a ring. The program itself, the tomography program, does it all for me, and I just step back and watch what comes out. So really, I became interested in it because I really needed to know if I was right. And in fact, it's really nice to know that it did confirm what I'd done in my PhD work, and I've extended that technique to many other systems since then. So that's a really very good question. Thank you. Yes.